Hello students, welcome to the fourth lecture in blackbody radiation in the quantum physics module of your physics course. So let's first summarize what we have discussed in lecture 3. In lecture 3 we discussed the Wien's radiation law and the Rayleigh-Jeans law which tried to explain the blackbody spectrum. But we have seen that they failed to explain the blackbody spectrum because the Wien's radiation law could explain the spectrum only in the short wavelength range and the Rayleigh-Jeans law could explain the spectrum only in the long wavelength range. It failed drastically at the short wavelength range, leading to the ultraviolet catastrophe in physics. So we discussed the failures of the classical laws of radiation. Now in today's lecture, I will talk about the Planck's quantum hypothesis which could explain the blackbody radiation, and we will also talk about the Planck's law of radiation, and we will see that in some limits we get back the classical laws from the Planck's law of radiation. So the failure of Rayleigh-Jeans law and the Wien's radiation law based on the classical theories of physics to explain the blackbody spectrum that led to a new theory in physics called the quantum physics. Using the law of equipartition of energy, Rayleigh and Jeans calculated the average energy of the oscillators, and with that they failed to explain the blackbody spectrum. So that brought in front of us the limitations of classical theories. So to overcome these limitations and to explain the blackbody spectrum, then Max Planck brought in a revolutionary concept in the theory of physics. So in 1900, Max Planck of Germany, he proposed the Planck's quantum hypothesis. So according to his hypothesis, the electromagnetic energy of the atomic oscillators can only be absorbed or emitted in discrete packets called quanta. And the electromagnetic energy emitted by these atoms is determined by the frequency nu of the vibration, and the energy released epsilon n is given by nh nu, where this n is an integer and h is the Planck's constant. So according to the earlier known theories of physics, the energy was of a continuous nature having all possible values from 0 to infinity. It was for the first time that Max Planck proposed this discrete nature of radiation. Now let's see, based on this Planck's quantum hypothesis, how the blackbody spectrum was explained. So we know that the energy density corresponding to radiations with frequency range nu and nu plus d nu is given by n nu d nu into epsilon bar, where this n nu d nu is the number of oscillators per unit volume contributing to the radiation of the frequency range nu and nu plus d nu, and epsilon bar is the average energy of an oscillator at an absolute temperature T. Now the calculation of n nu d nu remains the same as we have done for the Rayleigh-Jeans law, so it looks as 8 pi nu square by c cube d nu. But the difference is in the calculation of this average energy epsilon bar. So how was the average energy calculated here? So the number of atoms emitting energy epsilon n is given by n0 e to the power of minus epsilon n by kt, where this k is the Boltzmann constant. And this distribution is the Maxwell-Boltzmann distribution, the only known distribution at that time. So here n0 is the number of atoms at rest. The average energy of each oscillating atom, therefore, should be the total energy divided by the total number of oscillators. So the total energy is given by sigma 0 to infinity nn epsilon n, and the total number of oscillators is given by sigma 0 to infinity nn. Now what does this mean? If n1 number of atoms have energy epsilon 1, if n2 number of atoms have energy epsilon 2, if n3 number of atoms have energy epsilon 3, and so on, then this means n1 epsilon 1 plus n2 epsilon 2 plus n3 epsilon 3, and so on. And this is the total number of oscillators n1 plus n2 plus n3. So if we just put the expression of nn over here and epsilon n, it looks like this. And if we evaluate this series, it will look like h nu by e to the power of h nu by kt minus 1. So now we will put the expression of n nu d nu and epsilon bar in the expression of u nu d nu, and u nu d nu will look like this. Now just like our previous lecture, we know that the relation between this nu and lambda is c by lambda equal to nu, and d nu will be mod over c by lambda square d lambda, and we will express this in terms of wavelength lambda. So the energy density in the wavelength range lambda and lambda plus d lambda will be given by h pi 8 pi h by lambda to the power of 5 c by e to the power of 8c by lambda kt minus 1 d lambda. Now we have seen in the previous lecture that the energy is related to the energy density u lambda as E lambda d lambda equal to C by 4 u lambda d lambda. So if we put the expression of u lambda d lambda here, the energy in the wavelength range lambda and lambda plus d lambda looks like this. And this is the famous Planck's radiation law. Now let's see that how this law could explain the entire range of the blackbody spectrum. So let's see what happens to Planck's law in the limit of short wavelength. In the limit of short wavelength, lambda tends to 0. So this term hc by lambda kd tends to infinity. So e to the power of hc by lambda kd tends to infinity. So the Planck's law now reduces to this. Because e to the power of hc by lambda kt is a very large term, so 1 is neglected here and it looks like this, and this is the Wien's radiation law. So in the limit of short wavelength, Planck's law gives us the Wien's radiation law. So just as Wien's radiation law could explain the blackbody spectrum in the short wavelength range, therefore Planck's law can explain the spectrum in the short wavelength range. Now let's see what happens to Planck's law in the limit of long wavelength. In the limit of long wavelength, lambda tends to infinity. So hc by lambda kd tends to 0. So this term, if we do the approximation, if we neglect the higher order terms, so it will look like 1 plus hc by lambda kt. So Planck's law now looks like this. The denominator becomes 1 plus hc by lambda kt minus 1. So the law becomes 2 pi c by lambda to the power of 4 d lambda by kt. And this is the Rayleigh-Jeans law which explained the blackbody spectrum in the long wavelength range. So Planck's law can explain the spectrum in the long wavelength range. So Planck's law can explain the spectrum both in the short wavelength range as well as in the long wavelength range. So definitely therefore it can explain the entire range of the blackbody spectrum. So let's see how the plot of the Planck's law will look like. So this is the Planck's radiation law curve, and we can see that it is exactly similar with the experimental curve. And if we compare this with the Rayleigh-Jeans law, you can see that the Rayleigh-Jeans law fits well in the high wavelength region. And this is the comparison of Planck's law with the Wien's law. You can see that the Wien's law fits in the shorter wavelength region. So we get back in the limits of the short wavelength and in the high wavelength the classical laws of radiation. So with this I end my discussion on blackbody radiation. The success of this Planck's quantum hypothesis led to the development of a new theory in physics called the quantum mechanics. It laid the foundation of the quantum mechanics. And later on, eminent scientists like de Broglie of France, Heisenberg of Germany, and Erwin Schrödinger of Austria, they developed the theory of quantum mechanics. And definitely you will be learning about the theory of quantum mechanics in your physics course. So I end my lecture today.